What's up everybody, welcome to another video, and I hope you're ready to flex those brain muscles. This video is an introduction to sequences, and I'm going to focus on two types of sequences in particular, and those are arithmetic sequences and geometric sequences. So this is mostly for pre-calculus students who are seeing sequences for the first time and dealing with these two types of sequences, and I'm going to do all kinds of different examples and kind of explain things as I go, so hopefully this video is helpful. So first of all, let's answer the question of what is a sequence, right? Because there's a chance that this is the first time you're seeing sequences show up in a math class. So what I like to do is use old ideas to build and come up with new ideas or relate them in some way, right? So we're going to take a look back at functions and remind ourselves what a function is, because it turns out that a sequence is just a special kind of function, right? So I can define a function in this way: f of x equals 3x minus 5. This function's domain is all the real numbers, so is its range. So we can plug any real number we want in, and what happens is this function takes that real number, multiplies it by 3, and then subtracts 5 and spits out an output, right? That's how functions work, inputs and outputs. Well, I can define a sequence in this same way, except instead of writing f of x, I'd write f and this little subscript notation, I'd write an n. But we usually just say this out loud as fn, right? So fn equals 3n minus 5. Now, what's the difference between this function and this sequence? Well, the sequence is still a function, but it's a function that has a domain of only the positive integers. So the counting numbers, essentially, 1, 2, 3, 4, etc., and so on, right? So with this function, I can plug in 1/2, I can plug in pi, I can plug whatever I want in, whereas the sequence, it's only defined on those positive integers. So how we'd represent plugging something into this function is we'd write f of 1. That's what we do with a function. That means, what do I get when I plug 1 into this function? Well, I get -2, right? Whereas with a sequence, we write f sub 1, and we usually just call that f1. Again, we usually don't say sub, we just say f1. And that gives us the same thing, and this is cool because this is the first term of the sequence. That's what we call it, the first term. And in general, whatever the n is, that's the term we're looking at. And that's what's unique about sequences, is that with functions, there's no sense of like order, whereas with sequences there is. We have a first term, we have a second term, we have a third term, and etc. So the second term of this sequence, I would just write a 2 there for n, that's the second term, and that's what I get when I plug 2 in for n. So I get 2 times 3, that's 6, minus 5, that's +1, and then I can write out the third term. So if you're ever asked to write out the first however many terms of a sequence, this is exactly what you do, right? Plug 3 in, I get 9 minus 5, that's 4. And it turns out that this is actually an arithmetic sequence. We're going to come back to it in a second, but hopefully this makes sense on what the basic idea of a sequence is. So now let's take a look at a couple of different ways sequences can be defined. So the first way is what I showed earlier when I defined the same sequence. And what we call this is a sequence defined explicitly, right? It's also sometimes called the general term, the nth term, the explicit formula, the closed formula. It has lots of different names. Whichever name you use is fine. But we call this explicitly because the sequence is defined explicitly in terms of n, right? So for example, to find the 25th term, all I need to do is plug 25 into n, simplify that down, and there we go. I have the 25th term of this sequence, okay? We can also define sequences recursively, and this is what we call a recursive formula. It has two parts. We're given an initial term, right, usually the first term, and then we're told the relationship between each term, and this depends on previous terms. That's why we call it recursive, right? So to find each term, it requires us to know something about the previous term, or sometimes multiple previous terms as they get a little more complicated, okay? So if I wanted to find that 25th term, I would need to know the 24th term. And to find the 24th term, I would need to know the 23rd term. So there are some limitations, right? With this explicit formula, we can jump straight to whichever term we'd like, but there are some really cool applications with this, and you'll see this when you get to differential equations. These recursive formulas come up. But it turns out that these two are the same sequence, just defined in two different ways. Remember, we said our first term of this sequence was -2. So if we start at -2, we can get the next term by just adding 3, right? Remember, we said the second term was 1, the third term was 4. So we can get to each next term by adding 3. So this is a way we can define the same sequence, but instead of explicitly, we can define it recursively. And this is going to come up, and I'll even do a few examples where we go from an explicit formula to recursive and vice versa, so we can get some practice. But these are the two different ways we can define sequences. So remember when I said the sequence we're looking at is indeed an arithmetic sequence? Well, let's talk about what that means. So an arithmetic sequence is a sequence where the difference between any two consecutive terms is a constant. We call this constant d, this is what we use to notate it, right? D, the common difference. So that means if I take the first term and I take the second term, the difference between those two terms is a constant. And by difference, I mean that I can take a2 minus a1, and that's going to give me the common difference d. And in general, I can take an plus 1. So I can take any term and subtract the previous term, and that's going to give me the common difference, right? That's in general, any two terms. Okay, so it turns out that that does work for the sequence an, and we can prove it by looking at the n plus 1th term and the nth term, right? So let's real quickly do that, because occasionally you'll be asked to show that a sequence is indeed arithmetic, and this is exactly what you'll do. You take an plus 1, which is just plugging in n plus 1 for n, right? So an plus 1 is 3 times n plus 1 minus 5, and then we're going to subtract an, which is just the sequence itself, right? Replace n with n, it doesn't change. So 3n minus 5. And remember to keep your parentheses here because we're subtracting this whole thing. This negative is going to carry over here. So let's distribute this 3. We get 3n plus 3 minus 5 minus 3n plus 5, right? Minus minus gives us plus. So now look what happens. We get a lot of canceling happening. Minus 5 plus 5, 3n minus 3n. We're left with a constant 3. And it turns out that that 3 was our common difference. Remember when we found each term, it was just by adding 3 to get to each next term. And as a general hint, your common difference with these arithmetic sequences is what's going to be in front of the n, right? Because as we increase n by 1, the value of the entire sequence increases by whatever numbers in front of n being multiplied. So that's a general hint, but if you want to check for sure, I definitely recommend doing this. But yeah, that's arithmetic sequences. We're going to dive a little bit deeper into this and look at the recursive formula as well as the general explicit formula for these arithmetic sequences. So sometimes we are given either the terms of a sequence or just some information about an arithmetic sequence and asked to come up with either an explicit formula or recursive formula for that sequence. So these are both general formulas for arithmetic sequences defined explicitly and recursively, and I just figured I'd show them and show a quick example, although I don't think you really need to memorize either of these. As you're going to see through doing examples, it's not really required, but I figured I'd show it anyway. And let's look at the example we've been looking at. Let's look at this an equals 3n minus 5. And remember we said that the common difference was 3, and we found the first term. That was negative 2. So let's plug in this 3 as the common difference and this negative 2 as the first term and make sure we get an equals 3n minus 5. Like, let's just verify this and make sure it works. So an equals, remember the first term is negative 2 plus this n minus 1 just stays n minus 1 and our common difference goes here. And when we evaluate this or simplify it, we should end up with 3n minus 5, but let's double check. Minus 2 plus this 3 goes to n and to negative 1. So 3n minus 3. And these minus 2 and minus 3, those combined, they are like terms. So what I end up with is an equals 3n minus 5. So you can use this formula if you're given either terms of a sequence or you're given the common difference and the first term. You can go to this formula. I do it a little bit differently, as you're going to see through the examples. I do a more intuitive kind of exploration method, I guess. But this formula works well, and this recursive formula is pretty straightforward, actually. If we're given a first term and we're told the common difference, we know that we can get to each next term by just adding that common difference, right? So we've already seen that our a1 equals negative 2 in this same example. And we know that because the common difference is 3, like the way common difference is defined, that means we can get to each next term by just taking the previous term and adding the common difference 3. So this is actually the recursive formula for this same sequence, which we already saw previously. But I wanted to explain why this general formula was the way it was. Hopefully that makes a little sense. Again, Don't put too much reliance into these. I would say focus on the intuition and understanding how these arithmetic sequences work, but we'll do some examples right now. All right, so here's our first example working with these arithmetic sequences. We're going to show that this sequence is arithmetic, find the common difference, and write out the first 4 terms. And I encourage you to pause the video and try this on your own if you're really trying to practice and learn this stuff. Then press play to compare your answer with my answer. So first we're going to show that this sequence is arithmetic. And remember, to do that, we have to show that an plus 1 minus an equals some constant, right? In other words, the difference between any 2 terms is a constant. And what's cool about doing this is not only do we show that the sequence is arithmetic, but we get the common difference from doing this. So we actually knock out 2 of these 3 things we're being asked to do. So let's go and do this. I'm going to do the work off to the right here. So remember, the n plus 1th term is just replacing n with n plus 1. So that would be negative 4 times n plus 1 plus 2. And then we're subtracting all of an. Don't forget those parentheses. Negative 4n plus 2. Okay? Now let's do some distributing here. This becomes negative 4n minus 4 plus 2 minus a negative 4n. So plus 4n, and remember that negative has to carry, so minus 2. So let's see, we can probably simplify pretty nicely here. Plus 2 minus 4n plus 4n. So we're left with a constant, negative 4, which shows that this sequence is arithmetic because the difference between any 2 consecutive terms is a constant. Remember, these n's are arbitrary, so this means it's true for any 2 consecutive terms. And not only that, but we found our common difference. And again, notice this pattern that our common difference is always what's in front of the n, right? That's the common difference. You can usually jump toward that as you get used to these, but this is our common difference, negative 4. Now we just have to write out the first 4 terms. So let's go ahead and do that down here. A1 is what we get when we plug 1 in for n, right? So when I plug 1 in, I get negative 4 plus 2, that's negative 2. And now what we can notice is that, remember, our common difference is negative 4. That means getting to the next term, I'll simply just add negative 4. So that's a little shortcut. Once we find this first term, we can just add negative 4 to get the rest of our terms. And if you don't believe me, you can still go back and plug it in. Let's plug in 2. We get negative 8 plus 2, that's negative 6, right? Works either way. And the 4th term, we just subtract negative 4 again. So we've done everything we're asked to do. We showed it was arithmetic, we found the common difference, and we wrote out the first 4 terms. All right, so here are our next couple of examples. Let's see if we can be given the first term of a sequence, the common difference for that sequence, and write the explicit formula, or the general term, and the recursive formula. So pause the video if you want to try this on your own. But remember, I did show some formulas for how to get these a couple of clips ago. And remember, I said you don't really need to memorize these. Once you get some practice, it becomes intuitive. And I fully believe that. And that's what I do to get both of these, is really more of intuitive, sort of like a method of exploration or a method of inspection, right? Because I know that for this sequence, since the common difference is negative 3, sorry, that means negative 3 is going to be in front of the n. That's the pattern. That's how it always is with these arithmetic sequences, right? So now I just need to figure out what I need to add or subtract out here to make sure that the first term is equal to 5, right? So the first term is what I get when I plug 1 in for n. So that's going to give me a negative 3 here. So basically I think about what do I need to add or subtract from negative 3 to get 5, and that is 8 plus 8. And now I can double check and make sure this works. When I plug in 1, I get 5. I have a common difference of negative 3, and I'm good to go. So you would have gotten the same thing if you'd used that formula I showed a couple of clips ago, but I prefer to do it a little more intuitive. I hate memorizing formulas, and I avoid it whenever I can. And this is one of those situations where I can't avoid memorizing the formula, so I just do it this way, right? And really the same with the recursive formula. If you understand how this common difference works, you know that that means that you can take this common difference and add it to any term to get the next term. So that means for the recursive formula, if we just start with a first term, then we can find any term by just taking the previous term and adding the common difference, right? I don't want to add though, I want to subtract because it's negative 3. So adding negative 3, which is the same as subtracting 3, and that's a recursive formula, and that also lines up with the formula I showed a couple of slides ago. So again, you don't need to memorize those things. Build some intuition and understanding around how these sequences work, and you'll be able to just kind of explore your way through it. And it's a lot more fun doing it this way than relying on formulas. All right, here's the last example we're gonna do working with these arithmetic sequences. So given two terms of an arithmetic sequence, can you find the first term, the common difference, and write the explicit formula or the general term for that sequence, right? So we're given the 8th term is 8, the 20th term is 44. Can we gather all this information? Pause this video and try this on your own if you want to challenge yourself to see if you can do this. But there's a couple different ways to approach this. I'm going to approach it by starting with looking for the common difference and using that common difference to find the first term, right? And that's really the benefit to us, is knowing that this is an arithmetic sequence, and that means to get from the 8th term to the 9th term, we're adding some constant. Well, that means that to get from the 8th term to the 20th term, we're adding some constant over and over. And to be exact, we're adding that constant 12 times, right? We're adding that common difference 12 times to get from 8 to 44. So repeated adding, that's addition, right? That means that 12 times this common difference is what we're adding to the 8th term, which is 8, to get the 20th term, which is 44. Now I can just solve this equation for D, and I have my common difference, right? So I can subtract 8 from both sides. Now I have 44 minus 8, that equals 36. And now I can divide both sides by 12. And 36 over 12, I'm running out of room here, but that does equal 3, and that is our common difference. And I want to note that there's another way to think about this. We could have gone straight to this 44 minus 8 over 12, right? We can think about this as, well, what is the total difference from the 8th term to the 20th term? Well, that's 44 minus 8. So 36 is the total difference from the 8th term to the 20th term. But that difference is happening over the course of 12 terms. So I need to divide that total difference by 12, and I get 3. So two different ways of thinking about it. Either way works. But our common difference is, in fact, 3. So D equals 3. And now how can we use that to find our first term? Well, we know that that means that we can subtract 3 to get from the 8th term to the 7th term. And we can subtract 3 again to get to the 6th term. So how many times do we need to subtract 3 to get to the first term? 7 times. So the first term equals this 8th term minus 7 of these 3's. 7 times 3, right? Repeated addition, that's multiplication. So 7 times 3 is 21. So I have 8 minus 21, which is negative 13. Yes, had a quick brain fart there. So negative 13 is our first term. Now we have our common difference, we have our first term, so writing the explicit formula is really the same as we've done in previous examples, right? We know that since our common difference is 3, we're going to have an equals 3n. And whatever else is here is whatever we, let me rephrase that. And now we just need to think about what do we need to add or subtract out here to make sure that our first term is in fact negative 13. So when I plug 1 into here, right, I get 3. 3 times 1 is 3. So I need to subtract 16 to make sure that my first term is negative 13. And you could have, again, used that formula I showed earlier. That's fine. This is the way I like to do it. So our explicit formula is 3n minus 16. We found the common difference, we found the first term, and we are done. All right, so now we're finally going to make the transition into talking about geometric sequences. So remember, with arithmetic sequences, the difference between two consecutive terms was a constant. We called that constant the common difference. Well, with geometric sequences, the ratio of two consecutive terms is a constant, and we call that constant the common ratio, right? And we write it as R. And basically what this means is that if we take a term and divide it by the previous term, we get a constant. And that constant is true for any two consecutive terms of the sequence, right? Another way to think about this that I kind of like thinking about it as is if we take a term and multiply it by this common ratio, we get the next term, right? Which I can clearly see if I just manipulate this equation, multiply both sides by an, then I get an times the common ratio equals an plus 1, the next term, right? So that's sort of how I think of geometric sequences, as this repeated multiplication. We're multiplying by something to get to the next term, whereas arithmetic sequences is repeated addition. We're adding something each time to get to the next term. And that's how I sort of separate these two types of sequences in my mind. But let's look at this example. This is a geometric sequence, but let's verify that it is and maybe write out like the first 4 terms just to get a little bit of practice, get a little warmed up. So we can verify that this is a geometric sequence by looking at an plus 1 over an. And remember, that's just plugging n plus 1 in for n. So I get 1/2 to the n plus 1 over 1/2 to the n. And now this looks a little bit crazy, and I'm thinking, how can I simplify this? But we just have to go back to our exponent rules. And knowing these exponent rules is going to be really useful when dealing with these geometric sequences. So remember, if I have x to the a over x to the b, if I have the same base, I can subtract the exponents. That's equal to x to the a minus x to the b, right? For example, x to the 5th over x squared, that's x to the 3rd, right? So I can use those same exponent rules here, and what happens is when I do top exponent minus bottom exponent, I do n plus 1 minus n, and the n's cancel, and I'm just left with 1. I'm left with 1/2 to the first power, which is just 1/2. So we do get a constant, and that is our common ratio. All right, so this is a geometric sequence, even though we probably already knew it was. And let's just write out the first 4 terms. So we have our first term here is 1/2. Our second term is 1/4, right? 1/2 times itself. I'll write them out over here. I'm kind of running out of room. Our third term is, remember, we take the previous term and we multiply it by our common ratio, 1/2. So 1/8. So hopefully you see the pattern here. It's this repeated multiplication. That's why geometric sequences always have n in the exponent rather than out in front being multiplied, because it is that repeated multiplication. 1/16, and you get the idea. This continues. And here we have looked at our first geometric sequence. Well, let's go ahead and do some examples. So these are the general formulas for how we define a geometric sequence explicitly. So the general term of a geometric sequence is an equals the first term times the common ratio to the n minus 1 power. And then recursively, we just have the first term, and then we have each term is the common ratio times the previous term. This recursive definition should make pretty intuitive sense, right? The common ratio, we know that we can multiply each term by it to get to the next term, and then all we need is the first term, and we have our recursive formula. That's good. This explicit formula, a little less intuitive in my opinion. There's another way to do it that I like a lot that is a little more intuitive, similar to what I did with the arithmetic sequences. I'm going to show both ways in this part of the video, and then you can decide which way you like better. So first, let's find the explicit formula given that the first term of this geometric sequence is 2 and the common ratio is 3. Let's see if we can find the explicit formula. So first, let's just use this formula, right? We know that an equals the first term, so 2, times the common ratio, which is 3, to the n minus 1 power. A lot of instructors will let you leave it like this, it seems like. Some of them want you to just have n in the exponent, but from what I've seen, this is a perfectly fine answer for your explicit formula. So you literally just plug this stuff in and you get it as long as you remember this formula. The way I like to do it is I like to think about, similarly to what I did with the arithmetic sequence, but I think about, okay, well I know r is going to be to the n power, and I know my first term is going to be 2. So what do I need to multiply this by to make sure that my first term is 2, right? Similarly to how I did the arithmetic sequence, I thought about what I needed to add or subtract. Now I'm thinking about what I need to multiply here to make sure that my first term is 2. And it turns out that that is 2 over 3. And although these may look different, if you use your exponent rules and you rewrite this 3 to the n minus 1 as 3 to the n over 3 to the 1, then you have 2 over 3 times 3 to the n. These are actually the same thing. It's pretty cool, right? So this is a little bit more intuitive, I think. It's a little more fun. But you can just use the formula, and you can find an explicit formula given a first term and a common ratio that way as well. Either way work. I thought it was cool to show both methods. Recursive, it's really easy. You literally just write a1 equals 2, and then write an equals 3 times an minus 1, and you have the recursive. The recursive is typically very easy, but that's how you define a geometric sequence given the first term and the common ratio. We've done it both explicitly, finding the general term, as well as recursively. So let's do a couple more examples. So here's an example. We're given this geometric sequence, and we're going to find the common ratio r of this geometric sequence. And maybe looking at this, you're thinking, well, isn't the common ratio just 5/2? And if that's what you're thinking, then that's good. That means you have a really good intuition around this already, right? But we're going to prove that it is indeed 5/2. We're going to look at a n plus 1 over a n. That's our common ratio, right? So a n plus 1 is just, instead of n here, we have n plus 1, right? So our common ratio r is 3 times 5/2 to the n plus 1 power over 3 times 5/2 to the nth power, okay? And why I like this example is because it really highlights the fact that whatever constant is out in front in here being multiplied does not matter when it comes to this common ratio, right? Whether there's nothing out there, or this is a 2 or a -5, whatever it is, when we write out an plus 1 plus an, it's always going to cancel with itself, right? So it does not affect the common ratio. And now what we have here is those same exponent rules we keep going back to. X to the a over x to the b, we can subtract exponents, and we get n plus 1 minus n, right? So really we're left with 5/2 to the first power, which is in fact our common ratio. So if you're immediately looking at these geometric sequences that are like pretty simple like this, and you're thinking, oh, common ratio must be 5/2, then your intuition is building around this and you're on the right track. Let's see if we can look at a couple more complicated examples. All right, so here's a little bit more complicated of an example where it may not be immediately apparent of what the common ratio is, but we're going to do the same thing. We're going to look at an plus 1 over an and find the common ratio. And this is where I encourage you again to pause the video and try this on your own. If you want to challenge yourself, then press play to check your work and compare it with mine. So an plus 1 over an, again, I'm just replacing n with n plus 1. So when I do that, I actually get 3 to the n plus 1 minus 1, and those 1's cancel. And this is just 3 to the n. Up here, I still get 2 to the n plus 1, right? Nothing cancels there, 2 to the n plus 1. So this is all my a n plus 1, right? So that's all in my numerator. In my denominator, I have an, which is already copied here. So I can just copy it down. There's no worries there. And now I have this kind of crazy looking expression here, but what I'm going to do is multiply by the reciprocal of the denominator over itself, right? Another way to think about it is we're flipping the bottom and multiplying across, essentially, right? So when I do that, I end up with this times 2 to the n over 3 to the n minus 1, and then I'm multiplying by that over itself, so it's going to cancel with this. Hopefully you're following what I'm doing. So now what I'm going to do is, again, it still looks a little bit crazy. I'm going to do sort of a regrouping because this is multiplication. I can move stuff around. I can swap these, and that's what I'm pretty much going to do. I'm going to group the base 2 things together and the base 3 things together and see if I can use exponent rules to simplify even further. So if I do that, I get 2 to the n over 2 to the n plus 1 times 3 to the n over 3 to the n minus 1. Now I can use my exponent rules. Remember, top minus bottom, right? Base stays the same. So when I use those exponent rules, I'm going to come down here. I get 2 to the n minus n plus 1, sorry. But remember, that minus has to go to everything. So really what I have is 2 to the n minus, minus n plus 1, so that negative carries. I just always write that out because students always make that mistake. They forget the parentheses, so that's why I wrote that out. But what I end up with is n minus n, those cancel, minus 1. So I actually end up with 2 to the negative 1 power. So that's what this whole thing is equal to, 2 to the negative 1. Times, we can do the same thing here, n minus n, those cancel, minus negative 1, that's positive 1, because again, this is around parentheses, I'm subtracting the whole thing. So times 3 to the positive 1 power. 2 to the negative 1 is the same as 1/2. So really what I have here is 1/2 times 3, which is 3 over 2, and that is our common ratio, right? So that's still what we have here, 3 to the n minus 1 over 2 to the n. So it seems like maybe it doesn't matter if 1 is n and 1 is n minus 1 or 1 is n plus 1 or something like that. And the reason why is because we can actually take this original sequence and we can rewrite it to where all we have is 3 over 2 to the n, and then we have a constant out in front, right? We can rewrite it doing some manipulating, essentially using exponent rules, specifically with this part here, right? Because that can be rewritten as 3 to the n over 3. We can bring the 3 out as 1/3, and then I think this whole thing is actually equal to 1/3 times 3 over 2 to the n, right? So it's pretty cool how we can manipulate these sequences and change them around. I don't know. I think this stuff is kind of fun, but this is our common ratio. And let's move on and see if we can do maybe 1 or 2 more examples. All right, so here are our last couple examples for this video. We're going to find the explicit formula of each geometric sequence. So we're going to find the general term, or the nth term, right? A-n. I want to find this explicit formula in terms of n for both of these sequences, which we can do, right? We have the first term for each sequence, and we're given enough terms and told it's geometric so we can find the common ratio. Then we can just use our formula and go from there, right? So how do we find the common ratio? We can take any term and divide it by the term before it, right? Any term divided by the previous term gives us the common ratio. So since it works for any 2 consecutive terms, why not pick the terms that are most convenient for us, right? Why not pick 1 and 4? So the common ratio is 1 divided by 4, which is 1/4, right? Let's make it easy on ourselves. Let's not divide fractions if we don't have to, right? This common ratio holds for any 2 consecutive terms. Let's make it easy. So an equals a1, the first term, times 1/4 to the n minus 1. And you could also do this the other way that I mentioned earlier and showed, but I think this is how my pre-cal students are being taught. So I'm going to be consistent with them and just use the formula for this part of the video, okay? So let's go to the next example. Our a1 in this case is -3. We can find our common ratio. Again, let's make it easier on ourselves by just picking 1 and -3. So our common ratio is -1 over 3. And when you have these negative common ratios, this is why I wanted to bring this example up, this is when you get that alternating, right? Because what happens when you take a negative and raise it to a power? Well, if that power is even, then we have a positive. If the power is odd, then we have a negative. That's why we do this alternating, because n is odd here, odd, even, and it alternates. It's kind of cool. You'll see a lot more of this in Cal 2. You'll get to like alternating sequences and series and stuff like that. But anyways, for now, let's just use the formula and call it a day. So an equals our first term, -3, and then we have this -1/3 to the n minus 1 power, right? And we can test this and make sure it works. Let's plug in 2 and make sure we get 1 out of this. 2 minus 1, that gives us 1. -1/3 to the first power, that's -1/3, times -3, that is +1. Yep. So you can verify it. I always recommend doing that, especially on an exam. But hopefully this makes sense. And that's all for this video. Sorry, it kind of dragged out a little bit. I didn't expect it to be this long. I just wanted to make sure I was thorough. But hopefully you enjoyed. Hopefully this will help you in your pre-calc class. Leave any questions or comments below. I'm happy to respond to all of them. Like and subscribe, share it if this video helped you. But most importantly, keep flexing those brain muscles. See y'all later.